Okay. Now, if we were to graph that, this is what the graph would look like. So that's what the graph would look like. As you can see, when, here's negative 3.5, everything to the right, the graph is defined on. The graph is in the domain, excuse me. Everything to the right is in the domain, mostly because everything to the right is below the graph. I mean, that we'll get into next time. But you can find the domain from the graph as well. Okay. And anything to the left here, right, is not below or above the graph, so it's not in the domain. That's a different story. But anyway, this is what the graph looks like. So, anything to the right of negative 3.5, you can get the output for. Just go up to the graph. All right, so we have that example. Any questions on this? Okay. Here's another one. This one's a little bit different, right? Because the square root now is in the denominator. I mean, the numerator is 11. We don't have to worry about that for now. So we want to know when, right, 2x minus 4 is greater than 0, right? We don't want it to be 0 because then we'd be dividing by 0. So we want to know when 2x minus 4 is greater than 0, strictly greater. So we have 2x minus 4 greater than 0. We have this inequality that we want to solve. Okay, so what do? We want to get x all alone. So we're going to add 4 to each side, right? And we get 2x greater than 4. Okay, that's good. But now we want x to be all alone, so we divide by 2. That's what we're doing here. And when we do that, we have x over here greater than 2. X greater than 2. So this inequality holds exactly when x is greater than 2. Okay, when x is greater than 2. So that's this interval from 2 to infinity. Okay, good. So this is what the graph would look like. Let me draw that in Desmos. I did that for the other class. So, wait, actually, hold on. Let me stop sharing this and share Desmos. There we go. Okay. So again, we're in Desmos now, right? So what we do is we have 11 divided by the square root. I mean, you could type it out, or you can just go to the keyboard here and get the square root down here. We have, 2x minus 4. And again, it's all x strictly greater than 2. So let me type x equals 2 for fun. Now let me zoom out a bit. And here's what the graph looks like. Okay, this is 2. So again, the graph is going to get closer and closer to x equals 2, to that vertical line. But you can see that's never actually going to touch it, though. It gets very close, though, if we zoom in, though. And that's what I'm doing. Okay. That's good. So 2 is not in the domain of this. I pressed the home key to get back to this. Notice also that it never also touches the x-axis. It gets closer and closer, but it never actually gets there. Mostly because if it touched the x-axis, it would have to be 0 somewhere. And that doesn't happen. Right? This is never going to be 0 because for this to be 0, the numerator would have to be 0. But it's 11. So that's what the graph looks like. All right, let me go back to the notes. Here we go. Here it comes. So we have this now. Oh, someone else. Okay. So wait, someone had a question. How do we know if it's greater than or less than? All right. See if we can get this. When you have basically the radicand, which is what's under the square root, you always want that to be greater than or equal to 0 if it's like this. But if you have it in a denominator of a fraction, such as this, then you just want it strictly greater than 0. I mean, sometimes the inequality might turn around if you multiply or divide by a negative. Okay, so wait, does that answer your question? Okay, good, you're welcome. Okay, I mean, again, everyone, if you have a question, don't be afraid to ask. But if you can speak into your mic, please do so, because I can't see the chat while I'm teaching, so. Yeah. All right, good question. Are there any other questions? Okay, again, also, if you ever need help graphing with Desmos, don't be afraid to ask me, I can help you. Not only that, Desmos, remember, you can download it onto your smart device. I have it on my smartphone. It's really nice. It makes my phone into a graphing calculator, essentially. So, all right. So here's another kind of function we're going to look at. This kind of function here is a polynomial function. And basically, it's what it sounds like. A function is a polynomial function in x. If the function, I'm going to call the function f of x. That's how this is read, remember. F of x, not times, f of x. If that function is equal to, is this. If f of x is equal to a polynomial in x. So a function f of x is a polynomial function in x if it's equal to this. If it's defined using a polynomial. Remember, the n here, that's the biggest exponent of x, right? And that's called the degree of the polynomial. Okay. What's nice about those functions is those functions have domain equal to the all real numbers. It's not like with the square root where it's not defined. It's only defined for some numbers. Polynomials are defined everywhere, which really makes sense if you think about it, because you could take any number and raise it to a positive power. So, I mean, how would you graph these by hand? We will go into that. It really depends on what the degree is. When n is 2, we have a quadratic function like so. We'll see how to graph that in chapter 3. I know we have Desmos, but it's still good to be able to graph by hand. I mean, you want the graphing software to be a tool. You don't want it to do the work for you. So, you want to be able to graph it by hand. Not only that, and if n is 1, then our polynomial function becomes a linear function. Wait, that didn't come out right. A linear function is a polynomial function when the degree, the n, is 1. We have this. And again, their domains, they all have the same domain, these polynomial functions. Their range, however, that's a different story. It turns out for quadratic functions, the range is not going to be all real numbers, but for linear functions, it will be. So basically, the range will depend on different things, like the degree and the coefficients, but that's a different story. We also have rational functions. That's when you have one polynomial function divided by another, like so. It's kind of like with rational numbers, they're just fractions of integers, right? Rational functions are fractions of polynomial functions. Now, what's the domain of this? The domain here, this is all numbers, all x, such that the denominator here, q of x, is not 0. such that q of x is not 0. Okay? That's what this is. And really, to find the domain, it's like what we said before. To find the domain, you set the denominator equal to 0, solve that equation, and the domain is everything else, basically. Good. All right. Okay, that's good. Here's an example. Let's find the domain of this thing. Well, for the denominator, right, we want to know what the domain is. So the numerator is just 1. The denominator is a polynomial. You know, it's a quadratic. Polynomial of degree 2, that is. So we set it equal to 0 and solve. I mean, you could use the quadratic formula, but let's try factoring it. This one's easy to factor, actually, right? You have 3 terms, degree 2. The leading coefficient's 1. So you want it's a special case of the AC method, right? You want 2 numbers whose product is 1, but the sum is 2. Well, of course, you can see that the 2 numbers are going to be 1 and 1. You know, 1 times itself is 1, and 1 plus 1 is 2. So this becomes x plus 1 times x plus 1, which is x plus 1 squared. And remember, when you have this equal to 0, you set each factor equal to 0. Although in this case, the factors are the same. They're both x plus 1. So we just have x plus 1 equal to 0. Subtract 1 from both sides. And we get, you know, we're solving this equation now. We get x equals negative 1. So the domain here is all numbers except x equals negative 1.